Okay, today we'll talk about the bisection method to compute sine and cosine. The bisection method, well, we want to compute accurate values for sine and cosine in the range from minus pi to pi. And there are many ways of doing it. This way is actually the simplest. We know how to calculate sine and cosine for many values. And we'll use these formulas for cosine and sine in the calculation of the bisection method. We can use the bisection method to find sine and cosine for any angle in the range from 0 to pi over 3. With the bisection method, you have to start with a range, with a target that's in the range. Suppose initially the target does not exactly equal any of the endpoints ever, which is typically the case. Those are knife edge cases. We'll talk about other cases in a moment. At each stage, the previous interval is split into two pieces. It's the lower limit to the midpoint to the upper limit. And the target's going to be in only one of these. And we'll call that interval the new ln/un. So by each iteration, we're getting rid of we're dividing it into two pieces. We're throwing away the unwanted piece. The piece that contains the target shrinks with each step. Eventually, the interval is so small that you have identified the solution. So we'll define a new variable, delta n, to be the difference between the upper limit and the lower limit. Delta n always shrinks by exactly 1/2 each iteration. That's important because delta n is simple. It doesn't depend on the target tau, and it can be pre-calculated. This sequence delta n is called a basis, because it can be used to build up any angle, like the bricks can build any building. It makes sense to redefine the sequence un as un is the lower limit plus delta. So the fundamental calculation is ln and delta. And this redefinition works in the knife edge situation as well. In the knife edge, we'll say ln is equal to the target, not un. Un will never equal the target. So the rule for creating the sequence ln is straightforward. If adding delta to the lower limit exceeds the target, then we don't want it. And we'll keep the old lower limit. But otherwise, we'll increment the lower limit. We can easily compute sine and cosine using the rules for computing sine and cosine for a sum of angles. And we continue until we obtain the desired precision. So exercise 1, compute sine and cosine using the bisection method. We'll compute for 3 values of the target: 1 degree, 1/160th of a degree, 1 over 3,600 of a degree. So let's go to the spreadsheet and see how this calculation would work. Okay. Now, the very first thing we will do is calculate these delta angles. And in fact, we would never have to calculate them again after this first calculation. They'll never change. And the delta calculation is essentially the same calculation we did in the previous video. We start off with 60 degrees. Cosine is 0.5. Sine is the square root of 3 over 2. And then we use the rule for dividing an angle in half. And the half angle formula for cosine is equal to the square root of 0.5 times the quantity 1 plus the lagged value of cosine. The sine variable is the old lagged value of sine divided by 2 times the current value of cosine. We bring those calculations down, and we actually have to compute quite a few rows because it takes quite a few to get the precision we want. So L and U start off at 0 and 60 respectively. The logic variable is if the old lower limit plus the delta exceeds the target, then we don't want it. And the value of the logic is 0. Otherwise, we do, and the logic is 1. So the L value, lower limit, is if the logic is 0, we keep the old lower limit. Otherwise, we increment it by delta. U is always L plus delta. So let's bring those calculations down. And if the logic is working, then we will see that L and U will converge to 1. And it looks like it's working. It's not working, though, as well as it could. We'll talk about that in a moment. It's just a little bit off at the very end. So sine and cosine start off at 0 and 1 respectively. And then for cosine, if the logic is 0, we keep the old value of cosine. Otherwise, it's cosine L times cosine delta minus sine L times sine delta. Sine value is if the logic is 0, we keep the old value of sine. If it's 1, then we use sine L cosine delta plus sine cosine L's sine delta. And if we copy that down, let's see if it calculates everything correctly. Yes, that is very close to the right answer. Very close, just off a little bit in the very last digit. And we'll talk about why in a moment, but first we'll change the target to see if it still calculates correctly for different targets. It will. Let's just try a different one. 1 over 3,600. Okay, it'll calculate it fine. But the reason why the logic goes just a little awry in this calculation, and we'll see it better when the target's back to 1. We should see the pattern 1, 0, 0, 0, 1, 0, 0, 0. And we do until right there something went wrong. What happened? Basically, it's comparing two numbers that are very close to 1, and it can't tell that one of them is just a little bit more than 1. And therefore, it makes a mistake. So we're going to try to see if we can find a way to change the logic. Perhaps modifying the logic of when to increment ln might improve the precision. Let's define a new variable, Rn, remainder of n. It starts off at tau, and then if Rn is less than delta, we don't do anything. But otherwise, we increment the lower limit by delta, and we decrement the remainder by delta. That's all we're doing to the logic. So let's do another exercise. Let's compute sine and cosine using the bisection method, but using the Rn logic. Same values. Does the new method change anything? Why or why not? Let's go to the spreadsheet and see. So here's the spreadsheet, and we're just going to copy the entire spreadsheet into a new sheet so that we can modify this calculation. We're not going to change very much. We're going to insert a new column, and we'll make it a little wider so we can see what we're doing. And then we'll call it remainder. The remainder starts at the target. The target's in cell A2 off to the left. And then it looks at the logic and it says, well, if the logic is 0, we're not doing anything to the remainder. But if it's 1, we're decrementing the remainder by the delta degree. And then the logic, it compares the remainder, the previous remainder, with the delta degree. And if the delta degree is bigger than the remainder, we're not doing anything. But otherwise, it's 1. And we bring that down. That's it. That's all we're doing to the spreadsheet. Did it do anything different? Yes. I can see that the logic is different all the way down to the very end. Now we'll try a different value for the target and see how it calculates, and it'll calculate it fine. But the reason why the new method works better is simply that the old method was comparing two numbers that were almost identical, and that caused problems because it's like taking a difference between two numbers that are almost the same number. But the new logic avoids that problem. It's comparing numbers that aren't that similar. Okay, time to close the spreadsheet. Thank you.